Hi, today we're going to learn how to do these complex calculations for the energy requirements for changes of state. In order to be successful doing these problems, you need to make sure you're aware of where you are on the heating and cooling curve as you go to solve the problem. For example, are you here on the flat part where it's a phase change and the temperature is not changing? Or are you here on the sloped part where you have a beginning and ending temperature? So for this problem and all of these types of problems, you're going to be given all sorts of constants. Notice how we have three constants now for the specific heat capacity of water. We have one for the ice, for the liquid, and for steam. In addition, we have two other constants that are in kilojoules per mole. So you're going to take the quantity of water at a phase change and convert it to moles, and then use these constants to calculate the energy requirements. So here's a lot of words that tells you what I just said, that you're going to look at the heating and cooling curve, figure out if you're within phase or if you're at a phase change. So within phase, what you're looking at is, are you down here where you're at the solid form, or in here where you're in the liquid, or up here where you're a gas? If you are at either of these places anywhere along the curve, you're going to be getting a delta T value. If you have a delta T, or change in temperature, you use the formula for heat. Heat equals mass times C times delta T. So the tricky part becomes picking the right C. If you're down here, you use C for the solid. If you're over here, you're going to use C for liquid. And if you're up here, you're going to use C for gas. You'll get your answer in joules, and you convert it in kilojoules by dividing by 1,000. If, however, you're in a phase change, melting or boiling, you're not going to be given multiple temperatures. You'll be telling it's boiling at 100 or melting at 0 or freezing, etc. So you're going to have to use those heats of fusion or vaporization and get moles from your quantity, and kilojoules will be what comes out. So if we look at number 23 that you had for homework this week, it asked you to calculate the total quantity of heat evolved for 10 grams of steam starting at 200. You're going to condense it, cool it, and freeze it down to ice at -50. So when you first read this problem, you could think it just used the formula for heat. You have a huge temperature change, but you have to remember that you're on the heating and cooling curve, and we're going to actually end up using all of these constants to solve this problem. So let's look. We start up here, we're as a gas at 200 degrees, right? And we're going to go down here to a solid at -50. Okay? So we have actually 5 calculations to do along the heating and cooling curve, and then a simple calculation at the end to make for 6, where we add them all up. So let's go ahead and start. First calculation. We're going to start up here. Because we're on the sloped part, we're going to use Q equals M times C times delta T. We have a mass, we have a delta T, and we have a C for steam given to us in the problem. So that looks like this. There's our value for C for steam right here, and there's our delta T. Notice how it's a negative number here because we are taking energy out, so we're going to go ahead and put these numbers in negative. You can put them in as positives and change your sign at the end, but either way, we're going to get an answer in joules that we convert to kilojoules by dividing by 1,000. All right, we've done one. Now we're here in the flat part. We want to condense those 10 grams of steam to liquid water. So we don't have a temperature change. So we're going to have to use the moles of water in 10 grams and the heat of vaporization. And so that looks like this. 10 grams divided by the molar mass, or using dimensional analysis, 1 mole times 18.02 times the molar heat of vaporization, 40.6 kilojoules per mole, giving you a final answer of 22.5 kilojoules. Again, we're keeping our negative sign because we're taking heat out. You can add the sign at the end. Calculation 3. We're now here on the slopey part, right? So we can use the C for water that we're familiar with, 4.18 joules per gram degree C. We have our same 10 grams, And we now have a delta T because we're going to go from here at 100 down here to 0. And there we go is the setup. Mass times C times delta T, still negative, taking energy out. There's our kilojoules. Fourth calculation, energy removed to freeze 10 grams of water at 0 degrees C. That would be along here. We have one temperature change, or one temperature, no change. So we're going to use moles, which we already calculated, and heat of fusion. So I'm showing you how to get the moles again here. We're just taking our grams, dividing by the molar mass, and this time we use the molar heat of fusion, 6.02 kilojoules per mole, and get our answer in kilojoules. And there it is. Okay, so we've done 4 calculations. We've gone down all of these numbers. We're now in the last spot. How do we get down to minus 50? Well, we're going to use Q equals M times C times delta T, and we use the C for ice. So just the same pattern that we've been following all along. Mass times C, notice how it's the C for ice, 2.06, times minus 50, because we're going to go from 0 to 50, and we get our answer in kilojoules, which we can convert. Our answer in joules, which we convert to kilojoules by dividing by 1,000. Getting tired yet? We're almost there. We've done the 5 major calculations. The last thing we need to do is add up all those energy terms. So remember, we started way up here at 200 degrees C, and we cooled it down to minus 50. So we've got 1, 2, 3, 4, 5, right? Calculations to do. 1, 2, 3, 4, and 5. And our last calculation then is to add all the numbers and get a final answer. And so if you don't like to put your negative signs on your problems as you go, you're welcome to say the words released when you're done. Remember, we talked about that in our first unit of the semester, that when you say energy released, it's exothermic and it has a negative sign. There's lots of ways to communicate the same information. So in the end, you started there and you made it here and you got the answer to that very complicated problem. Most of the problems aren't going to require all 6 steps, but you need to know where you are on this curve to figure out how much work you have to do. So good luck, and we'll talk to you next time.